All right, so we have this inclined plane with a couple of blocks on it, and our goal is to determine which angle we need in order for these blocks to remain at rest, just to get a little clear. If I make this angle too small, little m is going to be able to drag this big block over the edge. If I make little m too big, the tilt's going to be so great that big M will drag little m up and over. So there's this absolutely perfect angle where things remain at rest. And we're apparently supposed to solve for this in terms of big M and little m. You know, if it helps, I'm going to make up some numbers. I'm just going to say big M is 5 kilograms. Now here's what we'll do. I'm going to say that big M is 2 kilograms and little m is 1 kilogram. And I'm just going to set that aside, and I'm going to do everything in terms of letters to show you what's going on here. Okay, you don't need to do this. It's just a little psychological trick to show you that you can actually do things when there's pure variables. Now, one other thing I want to say. With this question, it looks a little scary and weird because there's no numbers. But the truth is, you don't need numbers. What you need is this process we've talked about before. This is an inclined plane. Don't try to invent new physics. So we know that R is always perpendicular to the inclined plane. Great. So that's where R is. So here we go. I know that R points like this, so I'm going to do the free body diagram for big M. I have R here. I have FG of big M. So then I'm going to get FG sine theta of big M. Sorry. Oh my gosh, that was really annoying. R FG of big M. This is FG cosine of theta of big M. And this is FG sine theta of big M. Again, sine makes you slide, cosine cancels contact. And then we have this tension force going like this. So notice these two are on the same line, and these two are on the same line. Again, with inclined planes, these are the axes. That's just how it is. Y-axis, x-axis, get that memorized. And then for little m, similar thing. We're going to have tension pointing up, and we're going to have Fg of little m pointing down. And so, since we are in equilibrium, we can actually set up some equations. So for big M, we have R minus Fg cos theta. Equilibrium means no acceleration. This balances to 0. In the y direction, we're going to have, we need to define what is positive and what is negative. So we're going to assume that going over the edge this way, in other words, moving clockwise, is positive. So for big M, that makes this direction positive, and for little m, that makes this direction positive, so that they kind of combine to have this sign. So any force that goes this way is a positive force, and for this one, any force that goes downwards is a positive force. So for setting up the x equation for big M, we have T minus Fg of big M times the sine of theta equals 0. So we isolate the tension as being equal to Fg sine theta. Let's go back to our original question. Our original question is, we know there's an angle that's absolutely perfect so that the boxes don't move. If we go smaller than this perfect angle, the system slides this way. If we go bigger than this angle, the system slides back the other way. We're trying to solve for that perfect angle. We want an exact number for it, and these are our masses. So this equation, we can't do anything with it. Do not try to solve it. Do not try to isolate it. Do not try to force numbers in there. Give up and move on to the next mass. So for this, we have downwards as the positive direction. So Fg, acting on little m, competes with tension, and the effect is that they balance. So we have mg minus t equals 0. So little mg is the tension. Now check this out. We have two equations to work with. I'll call this equation 1 and this equation 2. They both have tensions, and we can actually equate them. Now we're getting somewhere. All of this is Newton's laws, but we have mg sine theta equals little mg. The g's cancel, and I get that sine theta is little m over big M. So in terms of the problem, theta is the inverse, well, in terms of the problem, theta is the inverse sine of little m over big M. If you actually wanted to use our masses, like I gave you numbers, you'd actually get that theta is the inverse sine of 1/2, and you would actually get 30 degrees using the numbers that I worked out. But this is actually the answer that the IB is looking for on this question. That is question number 3.